Before we moving and starting our webinars, I'm going to introduce the chair for today is Professor Zongui Guan, who was leading a research group on lightweight composite material and structure in the School of Engineering at University of Liverpool. He's leading a budget of 4.8 million from European Union project with the consortium members from 6 countries to develop adhesive-free timber composite structures. He has a lot of publication, more than 140. He's leading a lot of conferences. He's a part, I think, a member of a board of journal papers, and he has given more than 60 keynote, thematic, and preliminary speeches in international conference. So now the floor is yours, Professor Guan, and I'm proud as your student here.
So thank you for your introduction, Dr. Leiji. And so what I'm going to talk about today is a dynamic response of fiber metal laminates subject to extreme loading conditions. First outline of my talk, I will give a very brief introduction and include the current applications of fiber metal laminates. And then we'll talk about impact tests. In later, of course, the modeling, I will cover both impact and the blast response of fiber metal laminates. And then a little bit further development of thermoplastic-based fiber metal laminates. So finally, draw a few conclusions. Uncertainties nowadays is kind of a buzzword. We have a lot of uncertainties in the current world. We don't know when and where accident, natural disasters, terrorist attack will happen. So what we can do is to design and manufacture blast and impact resistant materials and structures, and we can place in some key locations to protect lives, protect the infrastructures. So here I show kind of aircraft back to 86, I think is in Scotland. So this because as the bomb actually detonated inside the luggage container, which dragged make the crash and killed all people on board and also about 11 people on the ground. So if we can design luggage container to resist possible explosion, so we can actually prevent this kind of disasters. So this is a fiber metal laminates luggage container after blast test. So as you can see, it survived. And this is a part of fuselage being ripped off during flight. And fortunately, aircraft landed safely without any major injury. And also this air blast, again, aircraft survived. But in those kind of locations, in those key locations, we may experience this kind of incident. So we could place impact and blast resistant materials. So to avoid loss of life and also damage aircraft in those key locations. So this one just shows the aircraft wing use the fiber metal laminates, so we can have a very good impact resistance. So to develop impact and blast resistant materials and structures, usually we do experimental work, and also we do numerical modeling. But with numerical modeling nowadays, very powerful, so we can reduce number of tests, and then we do a lot of numerical modeling. Once modeling validated against the test results, we can use the model to help our design. So fiber metal laminates. So what is fiber metal laminates? So many is a composite and the metal. So with a certain stacking sequence. So for example, here we have two aluminium layers outside, and the middle is composite layer. And this is called the 2-1, and then 3-2. So we have three metal layers and two composite layers and 4-3. And the composite, we can have different, of course. We can have glass fiber, Kevlar, and the carbon fibers, and the alloys. So we can have aluminium, we can have steel, we can have titanium. So it depends where we're going to use it. But at the moment, we use just aluminium mainly used for aircraft. So major advantages for fiber metal laminates is a very high impact and blast resistance, long fatigue life, good corrosion and fire resistance, and a very good, very low weight to strength ratio. That's why we use fiber metal laminates for aircraft. And the flexible stacking sequence, so we can have different constituent materials and different geometry. I'll talk about the thickness mainly. So applications. So here I show, C-17 cargo door made from fiber metal laminates, and you can imagine the military vehicles drive up and down. So you need very good fatigue resistance and also impact resistance. Airbus A400M frames was made from fiber metal laminates, C-130 flaps. And this is the A380, which is the largest passenger aircraft in the world. So upper fuselage was made from fiber metal laminates. So 27 fiber metal laminate panels used, which cut weight by 30% in upper fuselage in comparison to just pure aluminium alloys, so which is greater than 1 ton. So this is 3-2 FML stringer. Now, fuselage, we use fiber metal laminates. Nowadays, the Airbus, the kind of narrow body aircraft, use fiber metal laminates. And battery case, so this is mainly just for electrical car battery case, we need a very good impact protection. And so there, I know some company in the UK, try to use fiber metal laminates, probably already, produced some battery case. And also people use titanium carbon fiber or titanium Kevlar fiber to make kind of fiber metal laminates to protect the satellite. Now, I talk a little bit about impact behavior from previous study. So this is kind of minimum energy to initiate first failure for fiber of the material panels. So we can say this 95 joule. So that is fiber metal laminates. Layer is 3-2. So which is much, much higher than other materials like pure aluminium 2024 T3, and also carbon fiber PEEK. So this is pure composite. Yeah. On the right of this chart, I show we have done some simulation based on using a validated model. So the blank line is 75 aluminium-based fiber metal laminates, and the blue one is steel, and the red one is aluminium 7075O. So as you can see, with the plate thickness increase and the perforation energy increase significantly for fiber metal laminates, which is well above steel and aluminium. So design of fiber metal laminates, of course, you have to satisfy kind of load capacity, stiffness, and the bonding. So this include the fatigue and the impact, and the material properties of constituent materials. You need to design. So what are you going to use? You use aluminium alloys, you use titanium, or use some ground application, use steel, and also what kind of plastic, fiber reinforced plastic. So you're going to use this carbon fiber, Kevlar, or glass fiber. So structure response, of course, you have to design under desired loading conditions, and the scaling effect. This is Professor Canterville talked about scaling effect in details yesterday, and the numerical modeling and the validation. This is quite important. Nowadays, we have very powerful computers, so we can make use of this kind of power to do a lot of parametric studies to help design. So that's you know, I talk about use validated model to assist design fiber metal laminates. So this is kind of you know, drawing show. The red one, you know, is glare, is fiber metal laminates, and the blue one is aluminium, just aluminium alloys. So we can say the glare with a lower weight, but other also other properties like static strength, fatigue, impact resistance, damage tolerance, and the flame resistance. They're much better than pure aluminium. Now I am going to talk about some test results. So this is different fiber metal laminates from 2.1, 3.2, and 5.4. So we have 2.1, 3.2, 4.3, 5.4, and 3 different aluminium alloys. So we can say they have this similar failure mode. This is a projectile impact. So we have a different Stanker sequence. So primary feature is the kind of delamination between metal layer and the composite layers. And we have cracks, of course. And this show the front face and the back face 3.2 fiber metal laminates, and also 5.4 configurations. Now is the force against the displacement. So we use high-speed camera to record the displacement, and also dynamic load cell to record the loading. So this is, again, there's 4 different Stanken sequences from 2.1 and 3.2, 4.3, 5.4. So we have paired lines. So the lower one is from static, quasi-static perforation, and the upper one, static upper one, is from impact test. So we can clearly see some dynamic effect. Yeah, this is a 70-75 based fiber metal laminates, again is from 2.1 to 5.4. You can see you use different aluminium alloys, we have quite a different impact resistance. So the 70-75, we get close to 30 kilonewton, the peak load. But 60-61 T6, so we get about 8 kilonewtons. So you can choose different alloys. You can even mix up. So you can use some layer maybe is titanium, some layers aluminium, and the composite, you know, you can also mix up. So that's the beauty of fiber metal laminates, very flexible Stanken sequence. So this is high speed, high velocity impact, so it's close to 100 meters per second. And we have this DIC recorded the bank phase displacement field. So with different times, so we can say the impact events start and then get a peak and then try to bounce it back. So this one is not fully perforated. Now I'm going to talk a little bit about titanium-based fiber metal laminates. So we have this surface treatment use the laser. The titanium surface treatment is quite important. You cannot use standard blast or even use etching, chemical etching. That's not a good enough. So here we use a laser, different laser fluence. So we have 1 to 5. So number 3. So that's a laser fluence is 4.54 joule per square centimeter. So that gives us highest shear strength. So that's highest bonding, and this is the roughness, here. So this is the test results. So the bank phase from 2.1 to 5.4, and they're pretty similar failure modes, but of course they have different thickness. Yeah. So this load displacement. So with this 4 fiber metal laminates, so from beginning and then reach the peak and then got start perforation. The projectile perforated gradually to the full perforation. And this is the perforation energy against the different Stankin sequence from 2.1 to 5.4. And this is comparison between aluminum-based fiber metal laminates and titanium-based fiber metal laminates. So we can say this specific energy absorption mainly just joule perforation energy divided by area density. So we can say aluminum-based fiber metal laminates has higher specific energy absorption. The reason behind, of course, aluminum alloys has much higher ductility, and titanium is relatively brittle. Now I'm going to talk about the modeling. So the modeling for fiber metal laminates, we have to model individual constituent materials. To model aluminum layers or metallic layers is very simple. So you just use a Johnson-Cook constitutive model and the damage law. So I don't need to spend much time to talk about that. So mainly I will talk a little bit more about the modeling of composite laminates. So in commercial code, you have 2D Hashim criteria. And if you use L-Styler, you may have 3D failure criteria, but they don't have control about the damage evolution, rate dependent. So we have to develop a user-defined subroutine. So to especially for impact and the blast through the thickness damage is very important. So here is a kind of a degradation of material stiffness. So we have the modulus related to damage variables. So this damage variables change from 0 to 1, and then you can imagine this stiffness matrix actually close to 0. So you lose load carrier capacity, so that element will be removed. Yeah, this failure criteria, tensile shear failure in warp direction and also in the weft direction. So that is a typical woven composite. We use this damage criteria. And through the thickness, through the warp, weft, and the thickness direction. So that's the failure criteria we use. And this is strain rate dependency. So here we have sigma superscript S, that is quasi-static strength. And inside the brackets, so we have some enhancement due to strain rate. So reference strain rate is 1 per second, but the current strain rate from impact, from blast is variable. So you can have maybe just 100 per second to tens of thousands per second. So you can see this is quite a large enhancement. If you don't consider rate dependent, you wouldn't be able to simulate especially blast response. So this is some material parameters we use for those quasi-static strengths and also R, this coefficient. So it's a damage evolution. So we have damage failure criteria, and also we introduce alpha 1 to 3. And if we, in our modeling, we use alpha 1 equal to 0.2, alpha 2 equal to 2, and alpha 3 is 1. But we also did a test, so we use all alpha 1 to 3 equal to 0. So we have this kind of blast failure mode. And if we use alpha 1 equal to 0.2, but alpha 2, alpha 3 equal to 0, so we have this failure mode, which is much closer to real blast failure mode. I mean, I haven't mentioned about the interaction. Of course, you have to define interaction between aluminum to composite. And also you could define an interaction between plies. So this is the modeling results. So we have broken line from numerical modeling and the sorted line from test. So we can say pretty good correlation we have achieved. So this is 2 aluminum alloys based fiber metal laminates. Yeah, so very good correlation. So from 2.1 to 5.4. Yeah. Now here is some animation. I show how the projectile we simulate to perforate fiber metal laminates. So on the top here is comparison between failure modes obtained from test, and the lower one is corresponding numerical modeling output. Of course, the numerical modeling output, we have some failed element being removed. So you kind of see the tip region. So that's been because it's been removed due to damaged elements. And I mentioned before this degradation. So this delamination you can see between metal layer and the composite layer, so it's being captured, and the cracks, so the cracks being simulated quite well. So now this animation I just show the projectile perforate through the fiber metal laminates. Yeah. So this one is the modeling of high velocity impact. So we have a DSA kind of a bank phase displacement field, and then we have FE simulation. So we say reasonably good correlation, but this is just this displacement, of course, a different time. So this is start to bounce it back, this one. So we say, this also displacement, you have some recovery. So this modeling is show different velocity, different impact velocity. So with high impact velocity, we've got the full perforation, and the lower one we get just perforated, and the lower velocity we get projectile actually bounced back. So you can see this. So this 246 fully perforated, yeah, and around 18 meters per second is just perforated, and then 75 is not perforated, so it's bounced back, yeah. Now this is a cross section comparison, so different impact velocities and different aluminum alloy based fiber metal laminates. So we say this kind of a central cross-section failure mode. So the comparison on the right is a FE simulation, of course. So we can say they are pretty well simulated, the failure mode. So once the model being validated against test results, we can use the validated model to do oblique impact. So here I just show different angles. So the angle we count is from normal direction and to so you turn clockwise direction. So the first one is kind of 15-degree oblique impact, and the second one is 30-degree. And then we have 45-degree. And the final one is 60-degree. So this is very shallow. So if you get lower than that, or higher than that, you get a problem. Yeah, so you cannot get fully perforated. Yeah. Now this modeling results on titanium-based fiber metal laminates. So this is titanium glass fiber, S2 glass fiber, PEKK composite. So this glass fiber PEKK prepregs actually being reduced in-house, produced in-house. So so many just students made this fiber made this prepregs. So we have very good correlation between test and the modeling. So we say the load displacement also is quite well, you know, simulated. Yeah. So it's 5-4 and 4-3. So both are a good correlation from failure mode and also load against the displacement. So failure mode is kind of a qualitative validation, and the load displacement is kind of a quantitative validation. Now is the modeling blast response. So we have on the left is from simulation, from modeling, and on the right from testing. So this kind of damage feature being captured. So we have very large deformation for aluminum. So this rotate, and also this cracks. I mean the brick splitting fiber, you know, from composite. So this another animation just show the simulation of blast. This is the 2-1. So you get this kind of simulation. So that's captured kind of a real situation. And now if we increase the thickness of fiber metal laminates, so from now 3-2, 4-3, and 5-4, so you say that we have quite a different failure mode. So 5-4 is like a puncture failure because the relatively thick fiber metal laminates, and we have higher kind of explosive mass. So this animation again is to show this failure simulation. You can say, you know, it's relatively localized perforation failure. Yeah. Now I'm going to just give a summary. So this fiber metal laminates have been introduced with their advantages and applications and the design issues. And then we cover perforation failure of fiber metal laminates subjected to projectile impact. So this talk of many just tests show that. And then 3D Hashim failure criteria together with rate dependency and damage evolution have been implemented in Abacus Explicit through VUMAT. And the failure features of fiber metal laminates have been captured. So that many just for both impact and blast response. So the models developed are ready to be used for further parametric studies to assist the design impact and the blast resistant fiber metal laminates. So next, this final bit is the thermoplastic. So we have a kind of in-house manufacturing rig to produce glass fiber, PEK or PEKK prepregs. So this kind of thermoplastic prepregs. I mean, thermoplastic is increasingly becomes popular because the thermoplastic prepregs has unlimited shelf life, and you can remelt, reshape it. So that's why we can use thermoplastic based fiber metal laminates to reshape. You know, so we can produce a sheet, flat sheet. So we have mold, so we can reshape it. So that's the whole point that we have this kind of thermoplastic based. So this is glass fiber, S2 glass fiber prepregs we produced. This is the carbon fiber prepregs. And also we add different nanomaterials inside. So we can play with the ingredients. So that's a redeformed fiber metal laminates. So we are going to develop. Yeah. So finally, I would like to thank my group members, Jin Fan and Jin Zhou, Jihan and Lashir Ali Reza. And So now I'm going to stop here. Thank you for your attention. Any questions?
Hi, Professor. We have one question from the attendees.
Yeah.
It says, thanks, Professor Guan, for the informative and interesting presentation. I have one question regarding the laminate design. What is the direction of the pre-preg layer? That's from Sumaya.
Yeah. Thank you for your question. Yeah, it's composite we use here is many two types. One is unidirectional, but unidirectional we stack as 0, 19, 90, 0. So this kind of stacking sequence. Also, we use a woven. So woven is already been is been knitted. So that's kind of laminates. We of course we tested different ply number. So we have 4 ply, 8 ply, 16 plies. So I hope that answers your question, stacking sequence.
Professor Guan, do you have a chance to change the direction to the 45?
Yeah, you can, because, you just cut your unidirectional pre-pregs. So the plies, so one ply you can have, say, 40 plus 45 minus 45, and you can have 90. You can have different angles anyway. So that's flexible.
Hello, Professor Guan.
Hello.
Thank you very much for the presentation. I really like all the simulations. Since I'm not expert of simulation, but I have two questions as an experimentalist. I would like to know what is the technique used to image the projectile, like the projectile effect on the laminate composite that you showed in one slide.
This one?
Yes.
Yeah, this so the top, is just use optical microscope, to take, so you need to cut your field sample through the central cross section. So you cut, and then you take optical images.
Okay. Are there any way to take video when the process is taking place? I mean, during.
That's good. That's good thinking. Yeah, that's good. I mean, if you, I don't know whether there is such equipment available, but what you can use X-ray CT. So, but that's going to be in situ X-ray CT. So during preparation process, and you can see through it. So maybe you can capture that.
Okay, so the only available.
I mean, I know people used to test kind of tension and compression, but as far as I know, there's no impact. X-ray CT machine. So the X-ray CT machine built with the impact droplet tower. There, as far as I know, I don't think there is such one yet.
Okay, but the other question that I have is the result that you show that the titania don't give a good idea, a good result. What is the aim to using this titania? Is it only for comparison, or there is other application for this kind of composite?
I mean, I think titanium is much higher stiffness, of course, but it's relatively brittle. So that's why the perforation energy is not as high as aluminium-based fiber metal laminates. But if you use, for example, if it's a Kevlar prepregs, or even use the Dyneema, so I think the situation will be changed significantly, because that is a much stronger composite, and the one we use is just a glass fiber prepregs. So maybe the strength between titanium and the glass fiber is quite large difference. So for fiber metal laminates, ideally you have better compatibility. That will be better.
Okay. Thank you, Professor Guan.
Thank you.
We have one more question from Mr. Kappel.
Yeah.
How important is it to model the contact or the adhesive behavior between the laminates and the composites?
That's very, very important. Yeah, you have to simulate this interaction properly, interface. So here because due to time limit, I didn't have time to explain. So we use a cohesive layer, so which is available in the commercial code. So cohesive layer between aluminium alloys and the composite. And also you can use a cohesive layer between composite plies. But if you do that, especially if you have many plies, and CPU time is too much. Very difficult to handle. Yeah.
Okay, and so you do experimental tests to extract that strength and stiffness for the cohesive bonds?
That's the good question. Actually, what we did, we have some quasi-static material data, but to test kind of impact blast, this kind of event to get interface properties, that's extremely difficult. So what we did, we used the inverse modeling. So based on the quasi-static data, so we use inverse modeling to identify those parameters, so stiffness and also strength, so normal and the two shear directions.
Okay, thank you, Dr. Guan.
Thank you. So any more questions?
Professor?
Yeah.
Just one quick question. I like that last slide you showed about the reversible FML in special using thermoplastics.
Yeah.
I'm just wondering about the damage, because once, for example, you've got the damage when you reverse, yeah? Because I noted the thermoplastic is a kind of a reversible one, but what about the fibers? What about even the metals? Did you work something in this direction? Have you seen something in this direction in terms of evaluating the damage when it's when the deformation is reversed somehow?
So this this kind of a reshaping. So what kind of temperature you're going to apply is very crucial. So the temperature, you cannot apply very high temperature because that's the resin will be melt, and you cannot apply very low temperature because this deformation, resistance to reshaping will be very high. So this need to have thorough research. So that could be our future research area, reshapable. Of thermoplastic.
This is something we're expecting to explore in the future, because I'm wondering actually the residual damage that it happens and when you reverse, if the behavior is about the same.
That's need to do proper research. So I mean, when you do the reshape, you're going to have some spring back. So this spring back, so the mold design, you need to predict how much spring back, so you can accommodate, use your mold design. Here we are not talking about very small angle reshape. We talk about maybe 90-degree up to. Yeah, so you cannot say, I want to have kind of 180-degree this reshape. I think that's very certainly will get damage. But for these panels, you don't, sometimes, I mean, at least they can use to make the door panel to tail wing, this, that will be fine. For the fuselage is fine because that's relatively, quite, it's a smooth, curvature, yeah.
I see. Thank you very much.